All right, so now kind of let's do a little math example involving the Carnot efficiency limit and the heat engine. So here we have a 40% efficient heat engine. It's operating between a high temperature reservoir at 1000 Kelvin and a pretty large cold reservoir at 300 Kelvin. The heat engine is withdrawing, it's a typo there, let me see that. It's 10 to the 6 joules per second, excuse me there. So it's 10 to the 6 joules per second from the high temperature reservoir. What would be the rate of loss of entropy from that reservoir? And what would be the rate of gain by the low temperature reservoir? You want to express the work done by the engine in watts, and what would be the total entropy gain of the system. So we know that the change in entropy, delta S, is given by Q over T, the thermal energy divided by the temperature. And in this case, we're calculating it for the high temperature reservoir, so that's H, and despite the typo on the last page, and I apologize for that, it's 10 to the 6th joules per second. So. And that reservoir was at 1000 Kelvin. This number always needs to be in Kelvin. And so you get 1000 joules per second Kelvin. And from the problem statement, the engine was 40% efficient, so only 40% of the heat removed here, QH, is being converted into work. 60% of this number is actually being ejected into the low side, low temperature sink. So we take the delta S of the cold. That's going to be only, it's 40% efficient, so it's going to be QC over TC. We weren't given a number for QC, but we do know it's 0.6 because of the efficiency, times 10 to the 6th joules per second. And then we divide that by T sub C, which in the problem statement, the low temperature cold reservoir was 300 K. So that gives us an entropy change, a delta S of 2000 joules per second Kelvin. So the entropy gain of the cold source is 2000 joules per Kelvin, and the entropy loss of the hot source is 1000 joules per Kelvin. That's part A. Part B asked again what was the work done by the engine in watts. And we know that the heat engine converted 40% of the input energy into work. So we've got that the input energy was 10 to the 6 joules per second. And we multiply that 0.4. So you get 0.4 times 10 to the 6 joules per second. And we know that a 1 watt is a joule per second. So it would times 1 watt equals 1 joule per second. Throw that conversion in there. And so we get 400 kilowatts. And so from that we see that a very common way to write entropy is actually in watts per Kelvin. Watts per Kelvin, because that joule second is just an energy per unit time, which is the power is the definition of the watt, watts per second. And then C, what's the total entropy gain of the system, total entropy gain of the system is going to be delta S total is equal to delta S of the hot plus delta S of the cold. So from a system perspective, remember the hot reservoir lost entropy, so that's minus 1,000 watts per Kelvin. And the cold source is what gained the entropy, so it has a positive entropy change. So we get 1,000 watts per Kelvin, or joules per second Kelvin, is the total entropy gain of the system.